Alright, so in this lecture we discuss about design consideration for the instruction. So we know that one the by ordering in the memory is determined, the hardware designer must make some decision on how the CPU should store the data. And this is the most basic means to differentiate ISA. And basically we have the three choices. The stack architecture, the accumulator architecture, and a general purpose register architecture. So in choosing one over the other, the trade-off are simplicity. That's gonna be the cost of hardware design with the execution speed and ease of use as well. So in a stack machine, an instruction and the operand are simply taken from the stack. So a stack cannot be accessed randomly, and it needs to be accessed from the top and going down to the bottom. On the other hand, an accumulator architecture, one operand of a binary operation is implicitly in the accumulator, and one operand is in the memory, creating a lot of bus traffic as well. The third option in our design, that's a general purpose register GPR architecture. So the register can be used instead of memory. So this one allows us to perform very fast and compared with the accumulator architecture. And so it's efficient implementation for compiler as well. And the result is in a longer instruction. Okay. So here the GPR architecture. So most of the system today are GPR system, and basically we have the three types of GPR architecture. That's memory where two or three operands may be in memory. The second type is that register memory, where at least one operand must be in the register. And the third type of GPR, that's the load store, where no operand may be in the memory. So the number of operands and also the number of available register has a direct effect on the instruction length. You can see some example later on. So in order to perform machine instruction, commonly we use stack machine. Basically, stack machine usually use one and a zero operand instruction. For example, the load and store instruction require a single memory address operand. The other instruction use operand from the stack implicitly. Okay, for example, the push and pop operation involve only stack top element, so that's implicitly understand the element gonna be taken out from the top of the stack. Another hand, the binary instruction, for example, add or multiplication, use the top of two item on the stack. We can see some example later on how the element gonna be taken out of the stack and perform the operation. So the stack architecture require us to think about arithmetic expression a little bit different from the way we perform the operation on the using the paper and pencil. Okay, so basically we are accustomed to writing expression using infix notation. For example, we have the expression z equal x plus y. So the operation in the middle showing that x plus with y, and the result gonna be assigned to z. Differently in the stack arithmetic require that we use the postfix notation. So basically the expression z equal x plus y in postfix notation, we can have z equal x, y, and plus. Okay, so this are also called reverse Polish notation, somewhat in honor to his Polish inventor Jan. Lukasiewicz. So what's the postfix notation? The principal advantage of postfix notation is that the parentheses is not used. For example, the infix expression z equal to x times y parentheses plus with w times u parentheses can become a z equal xy time multiplication w u multiplication and the addition in the end. So that the representation in a postfix notation of the expression up here. Okay. So in order for the stack machine perform the operation, we need to transform the infix notation to postfix notation. So let's consider the example. We want to transform or convert the infix expression of 2 plus 3 parentheses subtract 6 divided by 3, okay, to the postfix notation. So first of all, we have the summation right here that the 2 plus 3 that the in parentheses gonna take precedence, and we replace the term with the 2, 3, and addition next. Okay, so this term gonna be transformed into 2, 3 plus and subtract 6 divided by 3. The next step is that we're gonna transform the division operator. So we have the 6 divided by 3 right here. That's gonna take the next precedence. So we will replace 6 divided by 3 with the postfix notation. That's 6, 3, and division operator. So now the expression gonna become 2, 3 plus subtract 6, 3, division operator. Now in the last step, we have the quotient of 6 divided by 3 gonna be subtracted from the sum of 2 plus 3. So we're gonna move the subtraction operator to the end. So the notation in the postfix form gonna be represented by 2, 3 addition, 6, 3 division, and the subtraction in the end. Okay. Next, we're gonna show how to use stack to evaluate a postfix expression. So let's consider an example. We want to use stack to evaluate the postfix expression of 2, 3 addition, 6, 3 division, and the subtract that the expression in infix notation is mean 2 plus 3 subtract 6 divided by 3 as we saw before. So the first step using stack for evaluation postfix notation, we gonna scanning the expression from the left to the right and push the operand onto the stack, and until we see an operator, and we're gonna perform the operation. So in our example right here, first of all we scan and we see 2. So 2 gonna be a push onto the stack, and then we see number 3 gonna push onto the stack. That's gonna on top of 2, and then we scan next. We can see the addition operator. So at this time, we're gonna perform the operation. So in order to perform the addition operation, we're gonna pop the 2 operands and carry out the operation indicated by the operator. So basically we pop 2 and pop 3 out of the stack and perform the addition. So we get the results of 5 gonna be pushed back onto the stack. So the next step, we're gonna scan and also push the operands until we see another operator. So we scan 6 and we push onto the stack, and then we scan 3 we push onto the stack that's on top of 6. So the next one we see the division operator. We're gonna pop the 6 and 3 out and perform the operation. So we're gonna pop 6 and 3 out and carry out the operation and put the result back onto the stack. So but one of the note in this operation is that for the non-commutative operations such as the subtraction and division, the top stack element is always the second operand. So we have the 3 and 6 and the operation that division. So the top gonna be, so the top element of the stack is 3, always the second element, second operand. So we have the 6, 3, and division is mean 6 divided by 3, and we get the result is true, and we push back onto the stack. So the next step, we finding another operator that the subtraction. So the operation gonna be carried out by popping up the 2 elements, that's the 2 and 5. So again, that's a non-commutative operation. The second operand, that the 2 gonna be the second operand. So we have the 5 subtract 2 equal 3, and the result gonna be a push back into the stack.